Bom, boa tarde a todos, espero que estejam todos bem. Eu me chamo Miriam Cristina de Moura Garrido, sou professora do mestrado em Desenvolvimento Humano, e na tarde de hoje, na sua palestra do CICTED, nós temos o professor Dr. Amir Muhammad Saad, que agora aparece para vocês, o Dr. Amir. Eu começo primeiro agradecendo ao professor Amir, que tem algumas limitações, né? O fuso horário do professor é um pouco diferente, o professor está na Nigéria, acho que são 4 horas à nossa frente, né? Então, obrigada pela disposição do horário, obrigada pelo aceite, né, do convite do evento e por ter achado dentro da sua agenda de compromissos um lugar para falar conosco aqui no Vale do Paraíba, direto para a Nigéria. Enfim, muito obrigada. Agradeço também ao convite dos organizadores do CICTED, né? Esse evento que tem se tornado cada vez maior e buscado cada vez mais integrar pesquisas de universos diferentes, de temáticas diferentes, e prezando sempre pela qualidade do evento. Então, o meu obrigada aos organizadores do CICTED pelo convite na mediação e pelo convite ao professor Amir. Antes do professor Amir começar a sua apresentação, eu acho importante a gente localizar um pouco o currículo do Dr. Saad, que não é professor de formação, não é da licenciatura por formação. O Dr. Saad, ele é nigeriano, como comentei, ele fez Sistema de Informação na American University of Nigeria. Depois ele fez um mestrado em Ciência da Computação na Coventry University, no Reino Unido, e mais recentemente terminou um doutorado em Ciência da Computação na Poli, na Universidade de São Paulo, com o tema do qual ele palestra na data de hoje. O doutor tem algumas publicações bastante interessantes, como na 40ª Internacional Conferência sobre Plataformas do Oceano, no 27º Encontro Nacional de Inteligência Artificial, ocorrido de forma online no ano de 2021. Tem pesquisado Machine Learning, Offshore Platform, Failure Detections and Predictive Analysis. Atualmente, por isso a alcunha professor, né? Ele é um doutor em computação da ciência, mas atualmente tem atuado como professor na American University of Nigeria, onde ele se formou na graduação e agora retorna à universidade como docente, parte do quadro docente da universidade. Então, uma vez mais, obrigada, professor, pelo aceite. Estarei aqui para fazer as mediações, caso haja necessidade de alguma coisa, enfim, e caso haja comentários, fica sobre minha responsabilidade depois passar a você as perguntas, fique tranquila a respeito disso. Muito obrigada, boa tarde a todos.
Posso começar? Hello everyone, I would like to thank the organization and everybody for inviting me, and for everybody listening, thank you for spending your time. The title of my presentation is Methods to Detect Failure in Mooring Lines for Offshore Platforms. As earlier stated, my name is Amir Muhammad Saad, and I am currently Assistant Professor of Data Science at American University of Nigeria. So this workshop the agenda for today is as follows. We start with the introduction section, then we move on to the methods of mooring line failure, after which we talk about the problem of detecting mooring line failure. The proposed solution is then provided in the NEMO architecture section. The results of the implemented system is then presented, and I conclude in the conclusion section. Floating platforms in the offshore are used for exploration and exploitation of oil deposits in the sea, and these platforms are normally kept in the desired location with the help of mooring lines. However, mooring line failure can occur at any time, and it can lead to the platform drifting away from the desired location, which can lead to the endangerment of personnel around the platform itself, or lead to oil spillage, which is an environmental pollution scenario. Therefore, the need for early mooring line detection arises. Traditional methods of mooring line failure detections consist of visual inspections of the mooring line at a scheduled time. This is done with the use of divers or remote operated vehicles, also known as ROV. In the case of divers, at a certain depth, using divers is no longer feasible because of the pressure within the ocean itself. While in the case of using ROV, depending on the condition of the sea itself, the images returned can be very blurry. Another way of mooring line detection is by using sensors which are placed on the mooring line itself. These sensors include the use of load cells, which measure the tension of the mooring line, or the use of inclinometers, which measures the angle of the mooring line itself. In cases where there is a suspect of mooring line breakage, the angle of the mooring line before breakage and after breakage or suspected breakage is compared. If there is a big difference between those two, it normally indicates that there is a problem in the mooring line. And finally, instead of placing the sensors on the mooring line itself, sensors are placed on the platform. In this method, the platform motion is monitored instead of the mooring line. Due to the recent advancement of processing power and computers and the rise of artificial intelligence, specifically machine learning, real-time monitoring and failure detection of mooring systems are done. Therefore, detecting mooring line failure is a very complex problem, which is further complicated by the following. Depending on the platform draft refers to the weight of the platform. For example, in this image shown here, a draft 8, which is considered blasted, also considered as empty, in blue, when compared to a platform with draft 21, which is considered to be fully loaded in my case scenario, or in this case scenario, we can see the motions of the platform under the same environmental condition differs. For that with draft 8, which is blasted in blue and fully loaded in orange, we can see the motions of the platform differs. And furthermore, after a line breakage occurs, the frequency of the motions also differs, thereby signifying that when a line breakage occurs, the platform motion changes. Depending on the draft condition, it also changes. And also, we have to consider the sea condition. If the sea is rough or stormy, the motion also changes. Therefore, identifying exactly when a line breakage occurs becomes very difficult. The objective of this work was then to develop a machine learning model which was capable of identifying when mooring line breakage occurs based on only the horizontal motions of the platform. And these horizontal motions are surge, sway, and yaw motions. The machine learning model was also implemented to detect breakage for various draft conditions. That is, starting from draft 8, which we consider to be empty, to draft 21 when the platform is fully loaded. The proposed solution for the problem is presented here. However, before we go into the system itself that was developed, data generation and training was conducted for training the network. To generate the data, 7,000 environmental conditions from a weather station in Rio de Janeiro, Brazil, was recorded and collected. These environmental conditions were then fed to a hydrodynamical simulator known as Dynasm, which was created by the collaboration of USP and Petrobras. This Dynasm simulator allows for the simulation of the platform under different environmental conditions. Also, with the simulator, platform motions with and without mooring line failure were simulated. And finally, with the simulator, the motions under different environmental conditions, 14 environmental conditions to be exact, were simulated. Input to the NEMO system were the motions of the platform, and the output of our proposed NEMO system is the group or the class to which a mooring line breakage belongs to. That is in the scenario where there is line breakage. In cases where there is no breakage, it indicates that there is no breakage. All in all, input to the simulator or input to the system itself consists of the surge, sway, and yaw motions, which are the horizontal motions, and output of the proposed system is the group to which a platform motion belongs to. For the predictor model, a multilayer perceptron was used. A multilayer perceptron is a feed-forward neural network which consists of an input layer, one or more hidden layer, and an output layer. In our case, the MLP used some previous seconds of the 3D motions of the platform to predict some future motions of the platform motion. Here, the 3DOF are the surge, sway, and yaw. The MLP in the predictor model was trained and tested under different environmental conditions. For the training of the MLP, 3,000 environmental conditions were used. These environmental conditions contained no failure in them. And the 3,000 environmental conditions consists of 750 platform motions selected from 4 drafts, 8, 12, 16, and 20. The trained network was then validated on 1,500 platform motions without mooring line breakage. From each draft, 350 motions were used. And for testing, the network was tested on all the simulated platform motions with and without mooring line failure for all 14 draft motions simulated. Input to the MLP consists of some 600 previous seconds of the surge, sway, and yaw motions to the input layer of the MLP network, and output of the MLP network consists of 100 future motions of the surge and sway motions. In between the input and the output layer, 3 hidden layers were used. The first hidden layer consists of 3,600 neurons, while the second and third hidden layer consist of 3,600 neurons and 1,800 neurons respectively. All the layers of the MLP network used a ReLU activation function, while the output layer used a linear activation function. For each environmental condition given to the MLP, an error score was calculated. And for the error score metrics, the following error metrics were calculated. The RMSE, that is the root mean squared error, the mean and median error were calculated and designated for each environmental condition. These error scores were then used as input to the second part of our NEMO system, which is the classifier module. Therefore, the first module is the predictor module, which takes in previous motions of the platform to predict future motions. For each motion predicted, an error score is calculated and assigned to represent that motion. The error scores assigned is then used as input to the classifier module to determine the motion, the class to determine the group to which the motion belongs to. Result of our predictor model is presented here. Here, the RMSE error score box plot for 300 random environmental conditions from both intact and broken mooring line scenarios were used to generate this box plot. Here we can see for motions with intact draft and intact mooring line, their error score are no bigger than 2. This can be seen demarcated in the red box below. The error score of draft D8, which is draft 8, is not bigger than 2. The same behavior can be seen repeating for all cases where there is no moral line breakage. That is D8, D10, D12, D16, and etc. While in the case there is line breakage, for example, in D8 BLO1, that is draft 8 breakage in line 1, we can see the error score jumps to more or less between 6 and 8. The same behavior can be seen for draft 8 with breakage in line 09, which is D8-BL09. The error scores is greater than the motions without line breakage. All in all, we can see there is a clear difference between platform motions when there is line breakage and that without line breakage. Also, we can also see that depending on the draft of the motion, the draft of the platform, the error range differs. For example, when you compare draft 8 with line breakage 01 compared to draft 21 with breakage in line 01, we can see the range of the error score for draft 21 is bigger. This has to do with the weight of the error score and the weight of the platform itself and the error score assigned by the error calculator model of the system. Given that the root mean square error does not give us or does not signify a positive or negative sign, the mean and the median error score is used to show the signal of the scores. For example, depending on which line is broken, as can be seen here, in D8BL01, the error score gotten for the 300 platform motions is negative, while for breakage in line 09 for the same draft, the error score becomes positive. This same behavior can be seen for all other draft conditions, that is draft 8 with breakage in line 1, line 9, and line 12. Also, we can see depending on which line is broken, in this case, BL01 and BL12, the error scores are negative, while for BL12 and BL16 and BL18, the error score becomes positive. This has to do with the configuration of the moral line. So imagine configuration of the moral line. When the simulator was simulating the motions, the moral line that is line 1 was located to the left of the platform, while for line 09 was located to the right of the platform. So depending on which side the moral line failure occurs, the error score differs. The same behavior can be seen using the median error score, with the difference being the range of the spread of the error scores. Here we can see draft 18 BL01 has a large error score, error range, compared to draft 8 BL01. So, given that we can see that there is always a clear difference between cases with breakage and cases without breakage. Finally, the last module or the last module of our system is the classifier module. Input to the classifier module are the RMSE, mean, and median error of all the simulated platform motions. Okay. And for this classifier module, a multinomial linear regression classifier was used. The MLR is an extension of the linear regression, which allows for more than 2 categorical classification. And apart from classifying a data point to a group it belongs to, it also provides the % probability of making the classification. In our scenario, the classifier was configured to classify platform motions into 5 groups. That is, group no failure. In this group, there is no failure in the moral line, intact. Group failure in group 1, failure in group 2, failure in group 3, and failure in group 4. The NEMO classifier was trained on 80% of the platform motions, making 392 motions, and it was tested on 20% of the motions, making 98,000 motions, with and without mooring line breakage. Result of our implemented classifier is presented here. Out of the 31, out of the 800, out of the 900, and out of the 96,000 motions, it only misclassified 31 environmental conditions. This can be seen presented in the confusion matrix to your right. For example, when the classifier was classifying for cases for cases with mooring line breakage in group 1, it misclassified 3 motions to belong to group 2, 7 to belong to group 4, 8 to belong to group no break, which is no failure, and it had no misclassification for group 3. While it was classifying for motions with failure in group 2, it misclassified 2 motions to belong to group 1 and 2 motions to belong to group no failure. It had no misclassification in group 3 and 4. When it was classifying for motions that had failure in group 3, it had no misclassification error. While when it was classifying for group 4, where there is breakage, it only misclassified 8 motions to belong to group 1. And in the case of motions without failure, that is no break, it only misclassified 1. Therefore, signaling that the classifier found group 1 to be the most challenging group to classify. An example of the accompanying probability the classifier made is presented below. For example, in the first row, for this platform motion, the classifier had a 59% probability that the motions belong to group 1, while it had a 40% probability that the motion belonged to group no break, no failure. As you can see, the classifier is always in doubt between 2 groups or more. However, given that we configured the classifier to always take the class with the highest probability as the class to predict into, this is why the classifier misclassified this environmental condition. However, given that the classifier provides the probability, this information is useful to the personnel aboard the platform. Thereby, they can use this information to determine where they should concentrate their efforts more into. For example, if a scenario occurs, they know to check the mooring lines that are in group 1 and to check the mooring lines that are in group 1. There is a higher probability that is where the breakage is. The same can be seen in row 3. For this condition, the classifier had a probability of it belonging either to group 1 with 48% or group 4 with 52%. Here, they can check, the personnel aboard the platform can use this information to check the mooring lines that are grouped in group 1 and group 4, which helps in reducing the cost associated with inspecting mooring lines, for example. In conclusion, the objective of this work was to develop a network that was able to predict mooring line failure. Our proposed network was able to not only predict when mooring line failure occurs, it was able to predict for multiple groups. In our scenario, in our situation, 5 groups. And apart from multiple groups, it was also able to predict for multiple draft loads. In total, the network was able to use previous motions to predict future motions. The error difference between the predicted and the measured was then used as input to the classifier, which had a good enough classification accuracy. I would like to stop here and thank everybody for listening to my presentation. and I'll be open for any questions right now. Thank you very much once again.
Hello, professor. Eu vou falar em português, se o professor consegue entender parcialmente, qualquer coisa, eu traduzo novamente. Eu queria fazer alguns comentários. Primeiro, comentar que os meus colegas aqui da Unitau têm, enfim, agradecer a sua participação, acompanharam em alguns momentos, né? É um evento bastante grande, mas, sobretudo, a importância, e eu agradeço mais uma vez ao Dr. Amir Saad, a importância desse tema que fica na plataforma da TV Unitau, então poderá ser recorrido pelos nossos ouvintes, pelos nossos estudantes e por outras pessoas que se inscreveram que se inscreveram no evento ou mesmo que acessem depois no YouTube. Então, deixo aqui registrado o parabéns e o obrigado dos meus colegas em relação à sua fala. Eu queria destacar também, professor, a importância, a mim, né, que venho da área das ciências humanas, como nos agrada ver a importância do avanço tecnológico em harmonia ou em prol de um menor impacto no meio ambiente, né? Talvez a gente, da humanas, tenha, às vezes, perca um pouco essa percepção e tenha o costume de ver sempre a evolução tecnológica como algo negativo. O seu trabalho traz exatamente o oposto disso, né? Demonstra que o avanço tecnológico, ele pode ser usado para preservação ambiental, para recuperação, enfim, para uma série de fatos. Então, eu acho que isso é uma das muitas grandes contribuições da sua fala, a qual eu agradeço. E se o senhor quiser fazer algum comentário final, eu deixo aberto para você.
Obrigado por tudo, para ouvir minha apresentação. Desculpa, o português não é minha primeira língua, mas estou tentando. Apesar disso, obrigado por me receber.
Obrigada. Bom, mais uma vez, o Dr. Amir Saad falou aqui conosco nessa tarde. Ele atualmente é professor da American University of Nigeria, então creio que deve ter contatos profissionais. Para aqueles que estão interessados em entender de Marine Line, a tese também já deve estar disponível no banco de dados da USP. E, enfim, muito obrigada, Amir. Excelente noite. Sim.
Só para comentar. Tem alguns artigos que foram publicados pelo esse tema, se alguém quer ler, para ter mais entendimento, está aberto para tudo.
Muito obrigada. A gente deseja para você, então, além de agradecer, a gente deseja um resto de dia, de quarta-feira excelente para você aí. Muito obrigada, doutor.
Muito obrigado.